Math 102, Chapter 6, exercise questions. So I'm going to go through the usual student questions from Chapter 6 in Math 102. And you can see I have the questions I'm going to do for each section. So you might want to take a look here and see if one of the questions that I'm doing is one of the questions that you have. I will also timestamp each of these different sections so you can quickly scroll to get to the appropriate section. Section 6.1. First question we're going to take at is a 9 here, and we're trying to identify misleading graphs and statistics. So in question 9, identify the misleading information or presentation in each graph. Make sure your answer is complete and full sentences and fully communicates your thinking. All right, so we're taking a look at this graph here, and it says percent who agreed with the court. So it looks like this is a percentage over here on this side. We got the percentage, and we can see the Democrats, 62% agreed with the court. When we look at the Republicans, 54% agreed with the court, and independents, 54%. So one of your first immediate responses might be, hey, this adds up to more than 100%. You know, if we take 62% for the Democrats and 54% of the Republicans, that adds to more than 100%. But that's not the case, because this is just a percentage of each of those different political groups. So they could add to more than 100%, because we're talking about, 62% of all the Democrats polled here, and then 54% of all the Republicans. That's not the case. But what is the case is this is a compressed graph. Notice we're starting not at 0. Anytime you see a graph like this, and especially with bar graphs, if we don't start at 0, this is called a compressed graph. And what that does when we compress the graph is it makes it look like there's a greater difference between these groups. Notice if we just look at the bar graph, it looks like the Democrats are like 3 times more likely, or 3 times more in favor of this court decision than the Republicans. But when you look at the actual numbers from 54 to 62%, that's only an 8% increase. So there's only an 8% difference between Democrats and Republicans here, or independents for that matter. So it's really a small difference, but the compressed graph makes it larger. So the misleading information here is, we would say, okay, so we'd say the graph is compressed, and it makes it look like a large difference between the parties when it's only 8%. Question 10 here. Again, we're looking at a misleading graph or a statistic, and we're supposed to identify what's going on here. So let's see. So this is sales from the fast food chains, and so it looks like we've got a little pictograph here of Starbucks, Taco Bell, Pizza Hut, KFC, Wendy's, Burger King, and McDonald's. And the McDonald's looks like they're ruling the planet here. And the misleading piece of information here is this is a pictograph, right? Anytime you see a pictograph like this, it's usually going to extort the differences between the things they're comparing. And in this case, if we look at Burger King has, looks like, 13 or 14 if we followed this over there. Looks like maybe 12 or 13 million in sales, and McDonald's has, looks like maybe 41. Well, that's quite a bit difference. Definitely McDonald's has more sales, but it's not only the bar graph we get here. If we made bar graphs like this, the bar graph would look like this in difference, which is quite a difference, but not as much of a difference as when we make this big picture for the McDonald's M, because not only do we gain height with this, we also gain a bunch of width with the graph, and that's misleading. So let's see. Okay, so we'd say the pictograph makes McDonald's sales look much higher than actual reality here. All right, question 11. Identify misleading graphs or statistics here. So we're looking at food stamps and average participation. So we check over here on the left for a compressed graph, because that's a usual trick. No, it's not a compressed graph. Notice 0, 5 million, 10 million, 15 million. We're starting at 0, and we're going up by that much. Let's look now at the bottom of our graph. So we got Nixon 1974, 76, 80, 83, 93, 94, 2008, 2012. So you can see here's the misleading part. Anytime it's called cherry picking data. Anytime we're going through and plucking out specific instances and specific years, and there's no consistent timeline on the bottom there, then the data is most likely misleading because they're picking these years specifically to prove whatever point that it is they're doing, not trying to get an accurate picture of what's going on with the data. So notice there's 2 years of difference here between 74 and 76, then 4 years, then 3 years, then 10 years, then 1 year, and then we're going 12 years, and then 4 years. So you can see this is clearly just cherry-picked data. And so we would say, okay, the timeline at the bottom of the graph is not consistent. This allows the author to make the data say whatever he or she wants. Question 12 here. We're looking at the knuckleball velocity of R.A. Dickey. So they got a picture of him here, and you can see that in 2012, he had this speed, 77.3, in 2013, 75.3, and it looks like, oh my gosh, the speed of his knuckleball has dropped in half here. Well, not the case. This is another compressed graph. Even though we don't have any numbers here, you can clearly tell that this scale is off. If this is 2 miles per hour less than that one, and it looks like it's half as much, obviously they've compressed the data. Okay. The graph is compressed, making it look like his pitching speed is half of what it used to be. Section 6.2. And here we're asked to graph this equation y equals 2/5 x minus 3. And a lot of times students have trickier problems. A lot of times students have problems graphing when there's a fraction involved here. And so what we want to do is we want to work smarter here and not harder. So what we do is we look at the denominator of our fraction, which is 5. If we choose for x in our table multiples of 5, it's going to make life easy for us. For example, if I put an actual value of 5 in there, notice what I get. I would get y equals 2/5, and I'm going to write this 5 as a fraction, 5 over 1. That's x value minus 3. So see, if I pick a multiple of 5, what happens before I even start multiplying is I can divide out this common factor of 5, and I get this, y equals 2 minus 3, which equals -1. So you can see if I pick multiples of 5, the fraction just drops right out. So the next multiple of 5, if I looked at multiples of 5 going positive, I'd have 5, 10, 15, 20. Well, those values are outside of the range of my graph. So let's go the other direction. So if we go the other direction, we can pick 1, but 1 is not going to help us a whole lot here. That would be the next multiple here. But we would pick 0 perhaps, and then we could also pick -5 going in the other direction. So that's what I'm going to do. I'm going to pick 0. Notice if I take 0 times 2/5 here, if I put a 0 in here for x, I'd have 0 times 2/5, which is just 0. So that would give me -3. Let's see if I put a -5 in there. So let's draw a little space there. Y equals 2/5. Again, I'm going to write that -5 as a fraction minus 3. So let's see. So the 5 will divide out again, but leaving us with a -1 up top. So -1 times 2 would give us -2 minus 3, which would give us -5. So if I put a -5 in there, I got a -5 out. So now I've got my 3 values. So let's see if I can graph this. So over 5, graphing this one here, over 5 down 1. So over 5 in the x direction, down 1 in the y. Then over 0, down -3. And then -5, -5 in the x direction, -5 in the y direction. Put us right down there, and you can see my 3 dots are lining up, so I'm confident that I got this graphed correctly. All right, 6.2, question 16. You're a parent planning your daughter's wedding reception. You're going to pay $800 to rent the hall for the reception and hire a caterer that charges $20 a guest. So we've got this $800 to rent the hall, $20 per guest. Write an equation that you would use to calculate the cost of the wedding reception, where C is the cost and X is the number of guests. So we'd say, all right, so if C is our cost, well, we're going to have this $800 plus $20 per guest. Now, $800 doesn't change. We're renting the hall right off the top. But this $20 per guest, if we had 1 guest, that would be $20. 2 guests, $40. 3 guests, $60. So you can see what we're doing is we're repeatedly adding 20. Anytime we have repeated addition, we use multiplication to represent that situation. So we want to go 20 times x. And let's just double check that. Notice if I had one guest here, one guest, 20 times 1 would be $20. Two guests, 40. Three guests, 60. This is going to do it. So there's my equation. Okay, fill in the table below with each cost for the given number of guests. Well, 0 guests is still going to be $800 because we had to rent the hall. 50 guests, well, let's go calculate that. That's going to be 800 plus 20 times 50. So I take 20 times 50, which gives me 1,000, plus the 800. So it looks like $1,800 for 50 guests. 100 guests. Well, 100 times 20, that's going to add 2 zeros to 20. So that would be 2,000 plus 800. So that would be 2,800. 150. So I'll take 20 times 150. 3,000 plus the 800 would be 3,800. Okay. Now we want to make a graph. Part B here is to make a graph of these things. So we want to label our graph. We want to have our independent variable down here at the bottom. And the independent variable is the number of guests. And then over here, this would be the cost, because the cost depends on the number of guests. We always want to make sure we put our independent variable on the bottom. So let's see, for the number of guests, we want to at least go to 150. So let's say maybe if we made each of these increments 50. Let's see if I did that. Let's just try this out. Let's say if I made this 50, then these little tick marks would be 10, 20, 30, 40. No, that's not going to work. Just don't have the right tick marks. But if I made this one, each of those tick marks 10, then this would be 40. So 40, 80, 120, 160, 200. Okay, now on the left side here we have to have cost. Let's see, if we did this hundreds of dollars, this would be 100, 200, 300, 400, 500, 600, 700, 800. It's not going to work. We need to make it more than that. Probably make this either $500 a pop or $1,000 a pop. So let's see. Let's make it 500 a pop. And again, you can do anything you want to here. Let's see. Each one of these tick marks 500. So that'd be 500, 1,000, 1,500, 2,000, 2,500. Yeah, that seems to make sense. So let's see. This was 500, 1,000, 1,500, 2,000. So this would be $2,000. And then this would be $4,000. And this would be $6,000. And that's probably good. Let's put one more up there, $8,000. And again, your graph doesn't have to look exactly like mine, but we have to have a consistent amount. Each of these tick marks has to be a certain amount. Now let's see. If I had 0 guests, which is right here, then I'm going to be at $800. So just a little bit short of 1,000 there. There'd be my $800. Let's see, at 50 guests, which is going to be, 40, 50 here, I'm going to be at 1,800. So right there about. And then 100 guests, 80, 90, 100, I would be at 2,800. So here's 2,000, 2,500, so right about there. And again, I'm not being totally precise here, I'm just estimating, but I'm getting pretty close. And that's pretty good. We could use this now to graph our line for cost versus the number of wedding guests. Section 6.3, question 7. Estimate each function each function value from the graph. Sometimes you need to find f of x, the dependent value, and sometimes you'll need to find x, the independent value. So let's take a look here. So here are my x coordinates, and remember in a function notation we replace the y coordinates with f of x. So let's see, this is telling us now in question A to find the f of x or function value when our x value is 2. So I would come on my graph over here and I'd find 2. So here's my x coordinate, and we want to know what is the function value at that x coordinate. If you look up here, there's our function value. It looks like our f of x value there is going to be 1. All right. Question B. Now, when our f of x value is -2, we want to know what the x coordinate is. So if we go up here, now we're going to find our f of x value at -2. So that's right down here, 1, 2. Here's my f of x value. Now we want to know the x coordinate values there, and notice there are actually 2 of them. We've got one x coordinate over here. One of those would be x equals -1. And the other one is x equals +1. All right, question C. We're trying to find the f of x value when our x coordinate is 0. So here's where our x coordinate is 0. Let's erase some of this stuff. Here's where our x coordinate is 0. What's our f of x value? Well, it's right down here. 1, 2, 3, -3. All right, and now again, now we want to find the function value, the f of x value, when x is -1. So let's come over here. Here's where x is -1, and our function value there is -2. All right, 6.3, question 14. Interpret the graph below. Make sure your answer is complete and full sentences to communicate your thinking. Okay, so we're looking here. It says, title the graph, Earth Day in California. So we want to stop right now and say, okay, Earth Day, California, it's springtime, California, they're celebrating Earth Day. All right, now let's look at what's going on here with our graph. So over here we have megawatts. So that's like electricity used. And then here are times down here. This is 3/28 of 2009. And so these are the times of the day. And it looks like you can see we're going on kind of military time here. 0 to 24 hours. So this would be at midnight, and this is the following day at midnight. So now let's look at our graph data here. So we've got available resources forecast. That's the green graph. So this is what this green graph up there is. That's available resources forecast. And then the red is the actual demand. So we're looking at this graph, Earth Day in California, and what this graph is about is it's about power, the power that's being used in megawatts. And the green is the available resources forecast. The red is the actual demand. Well, what happens, the electricity grid is kind of an amazing thing, and the power companies have to deliver just about the right amount of power that's going to be used. So they can predict through data how much power a certain area will use on a certain day at a certain time, and then supply the electrical grid with that much energy. And so that's what this green line is. That's the forecasted amount of available energy. So what that means is in a normal day, this green line would be the energy use. But now on Earth Day, you can see the energy use is a lot less. So now we want to interpret this graph, and so that's what we want to say is that since it's Earth Day, people are conserving energy and trying to do a better job with the resources available, and you can see how much energy can be saved when people are conscientious about it. That's the graph here. So that's what you would want to write out in your full sentence here, is that Earth Day in California, people are being responsible, and the actual demand for electricity is much lower than the normal forecasted level of energy used on a given day in March, towards the end of March. Okay, so I don't have the question listed here, but we're looking at question 1 in 6.4, and what we're supposed to do is graph and find the slope of these lines. Okay, so let's take a look at C here, 1C. So the first point is 1 in the x direction, -2 in the y direction, so 1, -2. The next point is -3 in the x direction, 1, 2, 3, up 4, 1, 2, 3, 4. Okay, so let's go ahead and plot that line. Okay, now we want to find the slope, and remember the slope is the change in y over the change in x. So we want to look at how much y is changing and how much x is changing between these points. So if we look at how much y is changing, we're starting here at 4 for a y coordinate value, and we're dropping down to a -2. So that's a negative movement, in fact a -6. If we start at 4, +4, and come down to -2, that's a change of -6. Now let's look at our x coordinates here. So here we are as our x coordinate. Now we're going to move to the right. 1, 2, 3, 4 units to the right. So -6/4. Well, we want to write this as a negative slope, but we also want to reduce that 6/4. That can reduce down to -3/2. We can write that negative in the numerator. You could also write it like this, 3 over -2. Or you could write just the whole slope as negative, and then in front of the fraction, 3 over 2. And there's going to be times when we want to move that negative around. It's going to be an advantage to do that. In this case, it doesn't matter. Any of those three answers would have been fine. All right, 1D. So let's go ahead and sketch this graph. So the first point here, -5, -1. So we'll go -5 in the x direction, right here, and then -1. The next graph, we are going to go, next point, sorry, is +3, 1, 2, 3 in the x, -2 in the y. So let's go ahead and sketch this guy out here. Okay, so you can tell we're going downhill again, so we're probably going to end up with a negative slope here. Notice when we did this graph to the left, it was going downhill. We ended up with a negative slope. Same thing here. So we're anticipating a negative slope. Change in y, change in x. Let's go look at these changes. So if I look at my change in y, notice I'm starting at -1 here and dropping down to -2 there. That is a change of -1. Now if I look at my x change, I'm starting at -5, so that's 5 units to get to 0, and then 6, 7, 8 units altogether, so -1/8. And again, you could write 1 over -8, same slope, or -1/8. All of those are the same slope there, no matter where you put that negative. Okay, question 4. We're asked to graph this using the slope-intercept form. So remember, question 4. So we're looking here and we can see that our form of our equation here is the slope-intercept form, where m is the slope of the line and b is our y-intercept. Okay, so let's see. We start with our y-intercept, which in our form here is going to be +3. Tells us, okay. And now from that point, we're going to use this slope of 2. Notice the slope there is 2, not 2x. It's just the 2 that's in front of the x. The x is our variable in our equation. So slope is 2. We always want to think about the slope as a fraction, though. So let's think about that fraction as 2 over 1. So, and remember, that is change in y over change in x. So y is going to change 2 every time x changes 1. So if I go to my starting point, which was my y-intercept here, and I go a y change of 2, +2, so I go up 1, 2, then an x change of 1, that would give me that slope there. And I could go another point here, up 2 over 1, and that's going to be the sketch of my line. Okay, so now let's look at question 11. Question 11, we'd like to use slope-intercept form, but this equation is not organized that way. So what we want to do is we want to get it in this form first, then we'll be able to easily graph it. So to get it in that form, we want to get this y variable all by itself. So we want to isolate this y right there. kind of pretend like we're just solving for that y. So let's look at this equation down here, and let's solve that equation for y. When we do that, I think we'll have slope-intercept form. So let's see. I always undo addition or subtraction first, so I'd add 10 to both sides. 5y equals negative 2x plus 10. Notice I wrote the 10 in the second spot. The reason I'm doing that is because, look, I want my just number here, but I want my x coordinate there to be in the, so my x variable there to be in this slope-intercept form. So now I'm almost done, but now I got to get y by itself down here. So I'm going to divide everything by 5, and I think it makes it easier to divide each of these terms individually. Go through and divide each of the terms by 5. So over here on the left side, 5y divided by 5, that leaves us with y. Then negative 2/5 x plus 2. Once I get there, it's going to be easy to see how to graph this equation. So let's see. Here's my y-intercept, positive 2. And then I have this slope of negative 2/5. And you might be wondering where to put the negative. Well, it won't matter. We'll get the same graph either way, no matter where we put that negative. So let's think of this slope as negative 2 over 5. And just to show you that it won't matter, I'll do 2 over negative 5. And you'll see we'll get the same graph. So let's graph this one first. Change in y is negative 2. Change in x is positive 5. So I would come up here to my point. I go down 2, 1, 2, over 5. 1, 2, 3, 4, 5. So there would be the graph of my line. Now, had I gone the other way, up 2, 1, 2, and then negative 5, 1, 2, 3, 4, 5, I'd be at that point right there, and you can see that's why it doesn't matter where we put that negative, it still makes the same line. Okay, question 14. Notice we're missing a y variable in here. We can still graph this, but it changes things when we don't have a y variable. Anytime we have one of the variables missing, we want to solve for the variable that's there. So to do that, I'm going to divide both sides by 2. And then I'll get this statement. X is equal to negative 3. So what happens if I look at my t-table now, if my variables are missing, one of my variables are missing, that means there aren't any restrictions on that variable. In this case, there are no restrictions on y. We can pick any value we want to for y. But notice there are very strict restrictions on what x can be. X is always going to be negative 3. And we can pick any values we want for y. So I'll just pick easy ones to graph, 1, 2, 3, and you can see that I'm going to get an x-coordinate of negative 3, y of 1, x-coordinate of negative 3, y of 2, 3, and you can see we're going to get this perfectly vertical line here for that graph. All right, let's take a look now at the 6.4 classroom project. When swimming, you may have noticed an increase in pressure on your ears the further you dive under the water. The water pressure in a pool, lake, ocean, or any kind of tank is a function of the depth. So the pressure, it's telling us the pressure is a function of the depth that you go underwater. Students in a class at Kellogg Community College used a pressure sensor and measured the water pressure at various increments in the swimming pool. The data they found is in the table below. So let's just kind of go over this intro here again too. So basically what happens is, as we dive under the water, the pressure increases. Now as it turns out, it doesn't matter the size of that body of water, whether it could be a pond, a swimming pool, or the ocean. What really creates the pressure on your ears is just the water that is directly above your ears or directly above your body, not the volume that's around you. So it doesn't matter what size lake or body of water we're in, the pressure is going to be the same. So students at KCC measured the pressure as they went down in depth. They did this. We used to have a swimming pool at KCC, and they did this. So atmospheric pressure, meaning zero depth, we're not under the water at all, is 14.65, and notice they're given in this PSI, which is pressure per square inch. If we go down 1 foot, the pressure is 15.12 PSI. 3 feet, 15.82. 6 feet, 17.11. The first thing we want to do now is graph this data. So let's see, it's already organized for us. So our depth we want down here on the bottom because that is independent. The pressure that we experience depends on the depth. So that's why pressure is over here on the left side. Our independent variable, remember, always goes on the bottom. So let's see, at 0 feet, our pressure is 14.65, and we'll just estimate that to be right about there. Okay? At 1 foot, now we're at 15.12, and again, we're just making this thing climb up a little bit. We can't be super precise with this graph. 3 feet, 15.82, so we're almost to 16. And then 6 feet down, we're at 17.11. So 6 feet down, 17, about there. So there's our lines, and you can see we're going to make our graph like that. Okay? Next thing we want to do is calculate the slope between each pair of points in your table. Your group can divvy up the work to save you time. Well, if we're working at home, we're going to have to do all the points because we don't have a group to pass any of the work on to. So what we're doing is we're calculating the slope between each combination of these points. So if we look up here, the way we're going to do this is we want to know the slopes between this 0 depth. So we want to do, what's the slope between 0 and 1? Then we're going to do, what's the slope between 0 and 3? Do you see what I'm going to do is I'm going to take this one and compare it to all of these guys. Between 1, between 3, and between 6. We're going to have to calculate 3 different times here, 3 different of those combinations. 0, comparing it to these other values, figuring out what the slope is between those values. That's the first thing. And that's what you can see down here in our values. Notice this is between 0 and 1, then 0 and 3, and then 0 and 6. That takes care of 0 now. We've compared 0 now to all of the other depths. Now what we want to do after we've compared 0 to everything is now we want to go back and now compare 1 to everything, because we got to find the slope between all possible combinations of points here. So we've done 0, we can kind of check that one off. Now we're going to do the same thing with 1. Well, we're not going to compare 1 to 0 because we've already done that slope. When we compared 0 to 1, it's going to be the same slope, so we don't need to do that. So what we need to do now is compare 0.1 with 3 and then 0.1 with 6. And you can see down here we start by comparing 0.1 to 3, and then these are left blank for you to figure out what's left to compare. So we're kind of having you follow this pattern here. So we compared 1 to 3. Here we're going to compare 1 to 6. Now we are done with 1 at that point. So we can go like this. All right, 1 is completed. We don't need to do 1 anymore. But now we got to go to 3 and make comparisons. Well, we don't have to compare 3 to 0 or 1. We've already done it. So I'm going to leave that last one up to you to figure out what we need to compare in that 6th location. But anyways, all of these spots, all 6 of these locations are going to be a different slope. And so what you want to do is you want to find the slope between each of these points now. Remember, slope is change in y over change in x. So go ahead, now is a great time to pause your video player now and calculate these slopes, and when you get done you can come back and compare them to what I have here. One other thing you want to make sure we're going to do here, these values are not going to work out pretty and they're not going to work out as nice fractions. So in this particular instance, we don't report the slope as a fraction. We report the slope as a decimal. So as you're finding these slopes, just go ahead and write it down as one single decimal number. Okay, so I've gone through and calculated these, and hopefully you came up with the same thing. So for question 1 here, we have the values, the slope difference here. So we're starting at 14.65 and we're moving to 15.12, and we're saying what's that change in y? Well, to find that change in y with whole numbers, it was easy to count it up. Now if we got to actually do the decimals, it's sometimes easier to subtract. So we're going to take this 15.12 and subtract the 14.65 to get that difference. That will tell us the change. Same thing here, we're going to take for my x-coordinates 1 minus 0, which would give us 1 in the denominator. So when I do that subtraction and divide by 1, I get this as the first slope. When I do the same thing now with the second part, the slope change between 0 and 3, we get 0.39. Now listen, if you've missed these two questions here at the beginning, why don't you go ahead now and pause your video player and make sure you can calculate the next couple of these and verify that you know how to do this. Okay, rolling on with the next one, we get a slope of 0.41 and then 0.35 and then 0.398 and 0.43. So you notice that all of these slopes are relatively close to one another. You know, these values are all coming out the same no matter which combination of points I compare. And the reason is that this pressure versus depth is a linear or consistent thing. As we get deeper, the pressure keeps increasing at the same incremental rates. We call that a linear relationship, and that's what we're getting here, and we're actually going to be able to graph a line that represents this pressure versus depth. Okay, so now we're ready to do the next part of this. I kind of already alluded to this, question 3. Did the different slope values appear to be close to a similar number or close to the number? And then what you want to do in question 4 is calculate the average of all of the slopes. Now remember, to find the average, we add all those things up and divide by the number of things. Okay? Then we also want to look at, let's look at right here, question 5, after you do 3 and 4. Now look at question 5. Look at the graph and determine the y-intercept of the water pressure data. So let's do these next 3 questions. Pause your video player now, answer these 3 questions, and when you get done, hit play and see how I do them. Okay, did the values appear to be the same? Yes, they did. If we look back up here, you know, we've got a lot of these high 0.39s and a lot of low 4s, 0.41, 0.47. So we're looking at around 0.4 here, it seems like, somewhere around 0.4. Looks like the slope values were around 0.4. Calculate the average of those slopes. So we want to add them all up and divide by the number of things we have here. So let's go back up to this data here. Looks like we've got 6 different slope values here. So we want to add them all up and divide by 6. Okay, so when I added them all up, I got 2.448. Now I want to divide that by 6 because there were actual 6 pieces of information there divided by 6. And so it gives me this slope value of 0.408. You could write that one, or I think of a slope value here of 0.41 if we rounded it. Either of those 2 answers would be fine for my average slope between there. Okay? Now let's look at question 5. Look at the graph and determine the y-intercept of the water pressure data. So let's go back up to our graph here. Okay? So we're looking at our y-intercept, which is occurring right here. And we could look at our graph and go, oh, I'm going to estimate that to be such and such, but you know what? It's right here. If we have an x-coordinate of 0, that is going to be our y-intercept. Notice, if we have an x-coordinate of 0, we are right here on the y-axis. So that right there is my y-intercept, that 14.65. So the y-intercept, which we represent as b, is going to be 14.65. All right. Question 6 now. Using the average of the slopes and the y-intercept, write a function that models the water pressure as a function of depth. So this says pressure as a function of depth is whatever our slope is, which we've calculated. D is the depth. That's our variable, like x in our equation is a variable, so that stays D. And then B is our y-intercept. So to write this function, all we have to do is use the information we've already just calculated in questions 4 and 5. Okay? After we get this model, let's do question 7 as well. We're going to use our model to calculate the water pressure 100 feet below the surface. So go ahead, pause your video player now, and let's answer these 2 questions. Okay. So pressure as a function of depth. The pressure of the water in terms of the depth is going to be our slope, which we said was either 0.408 or 401. Either one you want to use, it doesn't matter. I'll be more accurate and use 408 times the depth plus the y-intercept there, which is 14.65. So this gives us now what we call a mathematical model. This mathematical model will tell us the pressure the water is at a certain depth. And so here we go. Question 7. Use our model to determine the pressure at 100 feet below the surface. So now we're going to find the pressure at 100 feet is going to be 0.408 times, now that's the depth, 100 feet, plus 14.65. And so we would say then the pressure at 100 feet down is, we'll calculate this. So I'm going to take 408 times 100 and add it 14.65 to it. And that would tell me the pressure at 100 feet is going to be 55.45. Now if you used 0.41 in here for your slope, you're going to have an answer that's a little bit different, but still very close to this answer. And remember, the pressure is measured in PSI. So we want to make sure we include those units on the end. Okay? Let's take a look now at questions 8 and question 9. Use your model to calculate the water pressure at the bottom of the ocean floor for where the Titanic sits. So the wreck of the Titanic sits, which is 2.5 miles underwater. So we want to do that, and then here it is in the coastal waters of Papua New Guinea. The seafloor contains copper, zinc, and gold deposits worth hundreds of millions of dollars. According to a recent article in the National Geographic, Nautilus Minerals hopes to launch the world's first deep sea mining operation 1 mile, so this is 1 mile below the surface. Calculate the water pressure of the mining operation. So let's go ahead now. We're going to use our model now to calculate these two different pressures. Remember that our model is written in the depth in feet, not depth in miles here. So we're going to have to do a little bit of work here to calculate using the depth in miles. And remember that 1 mile is 5,280 feet. Okay. All right, so the first thing we want to do is we want to change this miles into feet. So I'm going to take 2.5 miles times 5,280, and that will give me that this is 13,200 feet deep for the Titanic. So what we're going to do is we're going to calculate the pressure of 13,200 feet deep, plug that into our equation, times 13,200 plus 14.65. Let's see what we get. So I'm taking 13,200 times 0.408 plus 14.65 is going to be 5,400.25 PSI, and I think it's reasonable just to round it to the nearest PSI. 5,400 pressure per square inch would have been a fine answer there as well. All right, question 9. Here now we're 1 mile below, so we're finding the pressure then of 5,280 feet, which is 408 times 5,280 plus 14.65. Sorry, my penmanship's getting a little rough here. Hopefully with my voice you can follow along. So we're going to take 5,280 feet times 0.408 and then add to that 14.65, and we get 2,168 or 69 PSI if we round it to the nearest PSI. Now either of these cases, 5,400 PSI or 2,169 PSI, that's an intense amount of pressure, and certainly not a pressure that human being can withstand. So we're going to have some serious equipment and some serious submarines to go down to those depths. All right, section 6.5. Question 2. Ever wonder how archaeologists determine the age of a fossil? Carbon-14 is a radioactive isotope found in the air. It's harmful and is present in all organic life. So basically what happens as anything is growing on the planet or living on the planet, it absorbs this carbon-14. And so when the animal dies, it stops breathing and stops ingesting carbon-14. And so over long periods of time, the carbon-14 decays, leaving less carbon-14 in the fossil. The half-life of carbon-14 is 5,770 years, which means half of it remains after 5,770 years. So the percent of carbon-14 in a fossil can be found with the exponential function. And so here we have a nice exponential function saying that if I take 1/2 raised to the t over 5,770 power, it will tell me the percent remaining, and then t is the time in years. So basically what happens is after the animal dies, carbon-14 starts to decay, but it takes so long for this stuff to decay. In fact, for half of it to be gone, it takes almost 6,000 years for half of it to be gone. So we can use this function right here to determine how old a fossil is. So let's go ahead now and take a look. So let's calculate the age of a fossil if there's 5,770 is the time that we're looking at. So we're going to find this. So we're going to take 1/2 and raise to this power of 5,770 divided by 5,770. Well, 5,770 divided by 5,770 is just 1. So really what we get here is we get 1/2 to the first power. Well, anything to the first power is just that thing. So half of C14 remains. All right. Let's do the same thing now, except for a much longer period of time, 34,620 years. So if we calculate that, we'll have 1/2, and we'll take this power, 34,620 divided 5,770. Well, first we got to do that division to see what kind of an exponent we're going to have here. So we'll take 34,670 divided by 5,770 equals approximately 6.0086, so we'll just say 6. So this is going to be 1/2 raised to the 6th power. So now we want to take and use our scientific calculator. So if you got a phone, turn it sideways and you'll get the cool scientific calculator, because we want to take 1/2, which is 0.05, and we want to raise it to a power. And so you'll see either x to the y on your calculator, x to the y, or you'll see a little hat button. Either one of those will raise this 0.5 to a power. And I said 0.05. I want it 0.5. So 0.5, and I have an x to the y button. And I want to raise that then to the 6th power. And that's going to give me 0.0156, basically, of C14 remains. Now, if we wanted to use this as a fraction too, if we wanted to write this as a fraction, what we're going to do is we're just going to take 1/2 times itself 6 times, which means I can do this. 1 to the 6th power, 2 to the 6th power. This will give me my fractional answer. So also using that x to the y button, I'll take 2, x to the y, hit 6, tells me 64. So this is really just the fraction, 1/64. So either of these answers are decimal answer here, or a fraction answer, 1/64 of the carbon-14 remains. Explain your answer in exercise B what that means. So I think I just said that, you know, that 1/64 of C14 remains. And so there's our explanation, but here's kind of what happens now. So if we examined a fossil and we tested part of the bones there in our fossil, and we found that 1/64 of the original carbon-14 remained in this fossil, then we could gather that this fossil is 34,670 years old. Question 3. So we've got this function, f of x is equal to 2 to the x plus 1. Is an exponential growth or decay function? Well, look at the base of our exponent here. That's a number that's larger than 1, so this is going to be a growth function. Now we want to graph this. So let's see, let's start with 0 and kind of work our way in both directions, positive and negative. So if we started with 0 and we had this f of 0, that'd be 2 to the 0 power plus 1. Well, 2 to the 0 power, anything to the 0 power is just 1. So I'd have 1 plus 1, which is 2. So at 0, this guy is going to be 2. So at 0, we're going to get an f of x value of 2. Now, let's see, if I put a 1 in there, then I'd have 2 to the first power, which is 2, plus 1 would be 3. So over 1, we go up 3. Let's see if I put a 2 in there now. 2 to the second power would be 4. 4 plus 1 would be 5. So over 2, up 5. And you can see this thing is starting to take off now exponentially there. 3, 2 to the third power would be 8. 2 times 2 is 4, times 2 again is 8. 8 plus 1 is 9. So that's going off our graph. Over here at 3, we'd be way up here at 9. So somewhere up here, you know, somewhere up there. So I think it's safe to say that our graph is going to go like this here. Let's see what happens as we start to put negative values in there. So let's look at f of negative 2. That's going to be 2 to the negative second power plus 1. Well, let's see, 2 to the negative second power, what that really means is this fraction, 1 over 2 to the second plus 1, which is 1/4 plus 1. So it looks like at negative 2, we're going to be right here at negative 2 for my x-coordinate. We are going to be at 1 1/4, so maybe right about here. And then let's see, how about, so we say, what do we say here? This was 1 1/4, 1.25 or 1 1/4, either way. So negative 3, let's see if we put a negative 3 in here. That's going to be a negative 3. Then that would be, this would be a 2 to the third power, which then this would be 1/8 plus 1. So at negative 3, we're a little bit smaller, but not much. Okay, and so what's going to happen here is these fractions, as this power, this negative power, negative 3, negative 4, negative 5, negative 6, as we keep, you know, getting these smaller negative values, negative 4, negative 5, notice those are getting smaller, even though it looks like the negatives are getting bigger. We get smaller and smaller fractions here. Notice we had 1/4 the first time, now we have 1/8. The next fraction, when we multiply again, would be 1/16. And then the next fraction, when we multiply by 2 again, would be 1/32. So these fractions are going to get really small, but they're never going to go to 0. So what's going to happen is we're going to approach this line right here, this 1, but we're never going to touch it. So actually we get an asymptote across there, meaning our graph is going to approach it here, but never get close to it. So we said here this was 1 1/8. Sorry, to be consistent, we should have put 1 1/4 here. I think it's easier to see with the fractions what's going on here. And that as it gets really small, we're going to get close to 1. and approach that asymptote. Now, I forgot to answer this question down here, but that's a pretty easy one. As x gets really large, our graph here is taken off to positive infinity. Okay, part B, identify any horizontal asymptotes in the graph. I think we've already done that. That's the graph right here, y equals 1. Notice that was this line right here. This line going across there is y equals 1. That was our asymptote. Okay, question 4, f of x equals 1/2 to the x power minus 2 is an exponential growth or decay function. Well, notice our base here is smaller than 1, so that's going to be a decay function. And now they want us to graph this function. So let's again start at 0. So if I had f of 0, it's going to be 1/2 to the 0 power minus 2. Well, anything to the 0 power is just 1. So I'd have 1 minus 2, which would be negative 1. So at 0, we get a graph, a function value of negative 1. Okay, let's see what happens now as we start to put larger positive values in there. So let's say we do now the first power. Well, then I'm going to have 1/2 minus 2. Well, 1/2 minus 2 is going to be negative 1.5. All right, now let's try 2. Well, 1/2 times 1/2, which would be 1/2 squared, would be 1/4. So 1/4 minus 2 is going to give us negative 1 3/4. And if we put a 3 in there, we'll get 1/8 minus 2 would give us negative 1 7/8. So you can see what's happening here. As we get larger, we keep getting closer and closer and closer to this negative 2. And so that is going to be our asymptote line here. Because at 0, we were at negative 1. Then we're going to move to negative 1.5. Then negative 1 3/4. Then negative 1 7/8. So we keep getting closer here on this side. And we're going to approach this line, y equals negative 2. And so as we get large, we'll get close to y equals negative 2. All right, as we start to get smaller, let's see. Let's say f of negative 2 is going to be 1/2 to the negative second power minus 2. Well, first thing we do is deal with this negative on that exponent. We take the reciprocal of the base, so it's going to be 2/1 to the second power minus 2. Well, 2/1 squared, well, 2/1 is just 2. So if I square 2, that's going to give me 4. 4 minus 2 gives me 2 as my output value. So at negative 2, I've already gone off the 2 there. Let's see. Negative 3. If I change this up here to a negative 3, then we're going to have 2 to the third power now. And 2 to the third power, 2 times 2 is 4, times 2 again is 8. 8 minus 2 is 6. So let's see, at negative 3, we're going all the way up to 6. And you can see this guy is going to take off to positive infinity. Oops. Positive infinity as we start to get very small values. And this way we said was 6. Identify any horizontal lines in the graph. Yep, we have one at y equals negative 2. I don't know if I had that negative on there to begin with, but that was a negative 2. That's where our horizontal asymptote is. Okay, question 5. According to the U.S. Consumer Price Index, published by the Bureau of Labor Statistics, the graph below shows inflation rates from 2005 to 2015. So you can see our inflation rates here, 3.4, then 2.5, and then 4.1, 0.1%, 2.7, 1.53, so on and so forth. So these are our different inflation rates. Using a set inflation rate of 3% for the next 10 years. So we're saying, okay, every year inflation, or the amount or the cost of goods, is going to go up 3% for the next 10 years. Fill in the table for the average cost of a fast food meal. Use $6.50 as the average cost of a fast food meal today. So let's say by today's standards, we would say that a fast food meal costs $6.50. And we are going to use inflation of 3% to calculate what's going to happen over the next 10 years. So inflation of 3% is the same thing as a 3% increase. And remember, if we use our growth rate for that, the growth rate for a 3% increase is 1.03. So that's what we want to keep multiplying these fast food costs by to calculate this inflation rate. So we're going to take $6.50 times 1.03 to increase it 3%. That means at the end of the first year, that fast food meal is going to cost $6.69.5. We're going to round to the nearest cent here since we're talking about money. So $6.70. Now when I go to calculate though, I probably don't want to use $6.70. No, I have to use $6.70 or else it won't work out very well. 6.7, and I'm going to multiply that times 1.03 again. And then so 6.90 times 0.03 again. Sorry, 1.03. Then we're going up to $7.11. And you can see all we're going to do is keep multiplying by this 1.03. Okay? So we want to graph these values. So let's fill in this table here. I'm going to go ahead and fill this table in. Okay. So I went ahead and I calculated all the values in the table, just kept repeatedly multiplying by 1.03. So I went ahead and made a graph. Now we want to make sure we're consistent. Now the years or time is going to go down on the bottom of our graph. That's our independent variable. The cost of this fast food meal depends on the years from now based on this 3% inflation rate. And so then I just started making a graph. So what I did is I said every one of these tick marks will be 50 cents. You could have done $1, but I think having it spread out a little bit since these values are pretty close together made sense to go by 50 cents to me. So when I went by 50-cent increments, I got 0 up to $10. Then I just did every one of these tick marks is a year. You could have done every 2 was a year. That would have been fine too. But I just did that, and I did 0 through 10. So notice my first point was 650. My second point there, after 0 at 1 then, was at 670, 690, and I'm just estimating these values. Now, from our graph here, it looks like we are creating a linear graph, meaning this thing is going to keep going on at the same rate, but that's not the case. We know this is an exponential growth graph because if we look at the differences, look here, the difference between 650 and 70 is 20 cents and 20 cents. But notice here we jump to 21 cents and then 21 cents. So you can see as that rate of change increases, meaning it's not always 20 cents per year, it's going to keep increasing as we go. Because what's happening here is we keep taking 3% increase of a higher number. So the actual change will keep increasing. So when that situation arises, we're going to have an exponential growth graph here. And so you can see kind of at the end here, I put a little tail on the end to say and communicate, hey, this thing is an exponential graph. It's not growing at the same rate. So I kind of curved it up at the end there just to make sure whoever's reading my graph understood this was an exponential graph there. Okay, let's see. Question C. In our previous study, we calculated growth factors. What is the growth factor for a 3% inflation rate? Well, we already talked about that. That's 1.03 as our growth factor. Define the average cost of a fast food meal. 10 years from now, you could take the initial cost and multiply by that factor 10 times. And so here's the quick way to get to that answer. The long way to get to that answer was take that table and fill it all the way out to get to 10 years. We could have calculated it in one shot right here because notice this model, all it's doing is doing what we did in the table. We started out with a 650 and we multiplied by 1.03 10 times. And so we could use this model to calculate this cost. So we could say now C of 10 years would be 650 1.03 to the 10th power. Let's see. So I would take my calculator. If I'm using my phone, turn it sideways because I got to get an exponent again. So I take 1.03, raise it to the 10th power. My case, x to the y button. Your case might be the hat. Hit the equal sign. Leave that big giant number in there. Don't round it. Take that big giant decimal number. I mean, it's not that giant of a number, but it carries on forever. And we take that times 6.5. And it gives us then $8.74. Let's see how that compares to our table. Oh, spot on to the table. Yep, so very good. So that's the quick way to do it. Once we kind of see the pattern going on, we write this model. We write a model like this, and then we can calculate any number of years from now. So using this formula, predict the average cost of a fast food meal 25 years from today. So what we want to do is we want to find C of 25. So 6.5, 1.03 now raised to the 25th power. So let's see. 1.03 x to the y 25th power equals, leave that in there, times 6.5. And it would tell us then that this thing, fast food meal in 25 years, would cost $13.61. And that's assuming that we keep getting a 3% inflation rate. If inflation rates change, of course, that won't be accurate. Section 6.6. Estimate each function, 6.6, question 23. Estimate each function value from the graph. Sometimes you need to find f of x, the dependent value, and sometimes you need to find x, the independent value. So let's see. They want us to evaluate the function when our x-coordinate is 3. So we go over here, x-coordinate 1, 2, 3. There's my x-coordinate is 3. You'll notice the f of x coordinate there is -1. All right, now, given us that our f of x value is 3, what is the x-coordinate? So we're going to go on f of x here and find 3. So 1, 2, 3. There's my f of x value of 3. And you'll notice my x-coordinate there is x equals -1. All right, f of x value of -2. So down here at -2, looks like my x-coordinate is 1, 2, 3, 4. And then finally, tell us the f of x value when x is -2. So let's come over here at 1, 2. And if we go up 1, 2, 3, 4, that's going to be an f of x coordinate of 4. Question 27. The value of a new car declines or decays exponentially over time. Sam purchased a new car for $24,500 in 2020. The make and model that he purchased has historically decayed at a rate of 18% per year. Fill in a table to show the value of the car in 2020 after each year. Graph the data. All right, notice here, T is the years after 2020. So right now, this would be at year 0. Year 0 there. Okay, so now we want to calculate for 2021 with an 18% decay rate. So if it decays at 18%, that means that 82% is left. So our decay factor is going to be 0.82. So I want to take the value of the car here, 24,500 times 0.82, my decay factor, which would represent an 18% depreciation or loss of value, and that would give me $20,090. Now I want to go the second year on that. All I got to do is take and multiply by that same decay rate times 0.82 equals 16,473.80, and I'm just going to keep multiplying by this 0.82 to fill out the rest of the table here. Okay, so I filled in the rest of the table there with the values, just again by multiplying all the values as I kept going down by 0.82. Then I went ahead and graphed them, and so I just estimated, on the graph there as I made these things. But you can see this is an exponential decay graph because it doesn't keep decaying at this same steep rate. Notice it's starting out at a rate of decay like this, but notice down here it's now tapering or flattening out. So that's how we know this is an exponential decay rate. Another way would be is if we look at the values here and compare the loss in money as we went down. Notice from 2021 to 2022 we lost about $4,000, but notice down here at the end we're only losing about $1,000 there. So you can see that it's decreasing over time, the value that's getting lost from the car. So what is the decay factor based on this 18%? We already said that. That's 0.082. To find the value of Sam's car in 10 years, we could have just used this equation. C of 10. Plug this guy in there. So let's do that now. So we want to take, with our scientific calculator, we would want to take 0.82, and we want to raise it to the power of 10. Hit equals. We don't want to round this value, because if we round this value at this point, we lose our accuracy. So you leave that number in the calculator and multiply it times 24,500. And it gives us 3,000. Let's put a $sign on there. 3,367.47. And so it looks really close to what we did when we got up here in the table, when we were using the table there. Using this formula, predict the value of the car 14 years from now. All right, so 14 now. So we're going to take 24,500. Take our decay factor now to the 14th power. So 0.82 raised to the power of 14 equals, leave that value, multiply it times 24,500, and that would tell us that in 14 years the car is worth $1,522.51. All right, question 29. Graph this graph. G of x equals 2 to the x plus 1. Well, let's start with 0. That's always, I think, the easiest place to start. So if I have g of 0, I'm going to have 2 to the 0 power plus 1. Well, anything to the 0 power is 1. So I'll have 1 plus 1, or 2. Let's start going in our positive directions now. G of 1 would be 2 to the first power plus 1. 2 to the first power is 2, plus 1 would be 3. All right, G of 2. 2 to the second power plus 1. 2 to the second power, that's 2 times 2 or 4, plus 1 is 5. And then g to the third power. 2 to the third power is 8. 2 times 2 times 2 is 8. 8 plus 1 would give us 9. Let's graph this. So at 0, we're at 2. At 1, we're at 3. 2, we're at 5. 3, we're already at 9, so way up here off the graph, you can see this guy is taking off. So when it gets real large, this graph is taken off to infinity. So we've got an exponential growth here. Let's start looking at our negative values. G to the negative second, so I'd have 2 to the negative second power plus 1. So that's going to be, when I deal with the negative exponent there, I write the base as a reciprocal, so this is going to be 1 over 2 to the second power plus 1. Which is 1/4 plus 1. So at a value of negative 2, I get an output value of 1/4. So negative 2, about 1/4 there. When I take g to the negative third, that's going to be 1 over 2 to the third. Well, 2 to the third is 8, so that's going to be 1/8 plus 1, or 1 1/8. And you can see what's happening here is we're approaching 1. As this graph goes, we're getting smaller and smaller. These fractions are going to keep getting smaller, but they're not going to go to 0. So we're going to approach 1 here. As x gets real small, we're going to get close to, let's just say this, close to 1. We'll never actually get to 1. So that tells me that there is this horizontal asymptote there that we are not going to cross over. And that is the line y equals +1. So there is our horizontal asymptote, y equals 1.